Make our final speaker of the day feel super, super welcome. He's going to talk about zero-knowledge, proof-based, on-chain private voting. Put your hands together for Ahmad Afuni!
Hi. So I'll be talking about some joint work that we, the Aragon ZK research team, have been doing with Aztec as part of Nouns DAO's private research sprint. So I'll be introducing stuff, talking about the design and implementation and outlook for the future. So as an introduction, this is a bit strange. I actually need to go up and down here. I don't suppose you have a clicker that supports that, or maybe a keyboard, because else I can't really. Can any of you hit the down arrow?
I had that for me.
Maybe I'll snap my fingers.
Yeah, for me they had it.
Just go down. If I do this, go down.
So I'm sorry about that.
No, you want to go down? No. Yeah, there we go. I'll snap my fingers for the next one. So TLDR is we have a token-based voting system with stay over here. So we've got a token-based voting system. Voter anonymity is built in for life, hopefully. Votes are shielded till the end of the voting period, and everything is verified on-chain. Snap my fingers. No, just that. And so the ideal workflow is the following. We have prospective voters enrolled to vote. A proposal is made and put to a vote. And voters then submit their vote. At the end of the voting period, votes are decrypted, tallies computed, results are published. And diagrammatically, it looks like this. We basically have, so this right arrow basically goes towards the future. Register to vote, voting process is created, and then a whole bunch of votes are submitted. Private key is revealed at some later point in time, and that marks the end of the voting period. And then the results are computed and published. So let me go on to the design and implementation. Down. And here's an overview of how that goes. Down, please. We have a locally generated private key for enrollment. So here's the thing. You want to use your hardware wallet, most likely. You need some form of a private key to be verified in circuit to show that you actually, or locally on your computer, you need to do some computations, compute some signatures that may not necessarily be standard. So we have a separate private key for that. Please go down. We have a time-locked public-private key pair. So there's a time-locked service, we assume it's God-given, reveals a public key at the initial time, and at some later point in time, we get a private key. That way, the votes are actually encrypted to the end. Please go down. Votes may be submitted by anyone, so here's where the anonymity comes in. Anybody can submit a vote as long as they submit the relevant ZK proofs, verifying that they actually own the NFT that is associated with the vote, and also that they've actually enrolled to vote. So all of these things are linked together in a ZK circuit. Please go down. And all of this is based on verifying storage proofs inside a ZK circuit. Please go down. And here's how the setup goes. We have the Ethereum blockchain. We could have not Polygon in this case, but we have Ethereum. Please go down. We have a fixed ERC 721 contract, henceforth the NFT contract. We have a ZK snark proving system. In our case, for our setting, it's ultraplonk with an underlying field, the usual alt-bnt 128. An embedded curve, in this case, is baby jub, whose order, or at least a subgroup of baby jub, whose order should be small enough for convenience, and we should have the possibility of on-chain verification. We have a ZK snark-friendly hash function H, which is Poseidon for us. Another hash function H1 used for aggregation. And finally, a time lock service for verifiably random key generation in order to hide the votes. And there are a few contracts associated with this process. First of all, we have the registry contract. So all it has is a mapping from addresses to public keys, in this case, baby jub public keys. We have a voting contract, which is where all the magic happens, where you actually start a voting process, submit your votes, submit the results. And I mean, it has some built-ins, like the registry and NFT contract addresses, but then for each voting process, we need specifiers to actually specify the vote, and this is where the God-given public key comes in. We also have ballots stored in there, but suitably encrypted, and I'll go into more detail as to how that's done, as well as proofs of eligibility that are submitted along with each vote, and aggregation of votes as they come in. So we basically reduce these encrypted votes using this hash function H1, Ketchak in the best case for lower gas costs, but then Poseidon for better circuit integration. And finally, we also include the results after everything is tallied. And in addition to these two contracts, we have verifier smart contracts to actually verify these circuits, these proofs that are submitted. And so the workflow for each contract pretty much looks like this for each of at least the first two contracts, which call out to the verifier contracts. We run a computation locally on our machine, maybe in the browser someday, soon, hopefully, and generate a ZK proof. We submit the public inputs of this ZK proof computation together with the ZK proof to the contract. Things are verified and data is stored on the contract. And so let's go into each of the individual contracts. So registration is simple enough. The steps are as follows. You generate a private key, Z, on this embedded curve. You compute the corresponding public key, and then you submit this public key to the registry from the address owning the NFT. So I mean, you assume that pretty much everyone would enroll to vote, but this is where the, I guess, linking of addresses to votes stops. Because in the next step, the voting process creation, we do the following. Well, I mean, this will not actually give us anonymity just yet. Somebody has to start the voting process, and they would submit the following to the voting contract. First of all, the parameters relevant to the voting process, so title, description, vote choices, maybe yes, no, abstain, that's our initial implementation, duration of the voting period. They would submit, they would actually state that all of the registrations should be relative to some point in time, given as a block number. And I'll talk more about this later. It should be a recent one, the most recent one in the best case. And from within the contract, we can compute the block hash, but we can't actually pull out the state root or any storage roots within the EVM. Those have to be supplied. And this is where you have to submit these to the contract relative to block N. And you also have to submit a ZK proof that actually links this block hash over to the state root and also to those storage roots. And this will come in later when each person casts their vote. And in addition, we have to specify a public key which everyone would use to encrypt their votes. So the voting process will then go as follows. For vote V associated with address A, process ID being basically the process number, so the voting process number and the specifics of the contract to link it up to this particular voting process. And for NFT with ID given by ID NFT, the voter should do the following. First, compute signatures, so a signature involving the NFT ID and the voting process ID, and one involving the public key. Sorry, not the public key, the vote itself. The second step is to compute the nullifier from this first signature involving the ID of the NFT. This is to prevent double voting, much like double spending. I mean, it's the same trick. We generate a random private key R and compute a new public key A, and then a shared secret relative to this private key and the private key of the time lock service of basically the key used to encrypt the votes. We encrypt the vote V using this hash scheme, so we use Poseidon in our case, and we basically do it relative to the shared secret. And we then also obtain storage proofs, basically linking the address to ownership of this NFT with ID NFT, and also linking the address to the public key Z corresponding to this private key used to sign everything. And we generate a ZK proof pi of this whole computation, so basically we verify signatures, compute nullifier, etc. And we use these underlined quantities, so basically this public key A, the encrypted vote, and the nullifier. We basically submit those as public inputs, and finally we take all of this, we take the public inputs and the proof pi, and we submit those to the voting contract. And that's how you vote. And now, well, once the voting process is over, what do? How do we, compute the results? Well, at this point, we're given the private key corresponding to this public key used to encrypt all the votes. And we obtain ththese pairs, AI and BI, so basically the public keys for the individual votes and also the individual votes in encrypted form. And now what we can do is we can compute the shared secret because we actually have the private key corresponding, from the time lock service. And we brute force decrypt each BI to obtain the relevant vote. Then we can compute the results of the voting process. And then we compute the aggregation. So what happens is along the way, as the smart contract gets all the votes, it actually aggregates by basically reducing a list of all the submitted votes, encrypted votes, reducing it by means of this hash function h1, which is actually Poseidon in our current code, but it could just as well be Ketchak, depending on your trade-offs. And what we do is we generate a ZK proof verifying these steps with public inputs, the identifier of the whole process and these underlying variables. And then we submit this proof together with the public inputs to the voting contract to publish the results. So there are a few challenges involved in all of the above, and you may have already picked up on them. First of all, tri-proofs are very expensive in a ZK snark. So it actually takes, on the order of 10 minutes to do each of those proofs for the voting process and for actually, casting your vote. And there's also a gas proving cost balance. You have to strike a balance between gas cost and proving time or proof size, depending on what hash functions you choose, for example. And another challenge is saving the whales. So whales with tons of NFTs could cast a whole bunch of votes in quick succession, and then you'd be able to figure out who actually cast the vote, right? So you might want to hide the identity of a whale, so you might need a relayer service in between, time delayed, in order to, preserve the identities of these, just to hide the identities of these whales. So our outlook is that we're actually producing a proof of concept, should be out pretty soon. And we're looking at optimizing our circuits and all of our codes so that everything runs sufficiently quickly. There's also the other, let me go on to the next point. The last part of our outlook is DAO integration. Actually integrating this into a DAO, here at over at Aragon, we have our own DAO deployment framework, and it would be nice if if this could be plugged into the plugin system, and that is on our roadmap. This is pretty much where we plan to go, and I've actually gone through the whole talk, so thank you for your attention.